Hello, Math 3 students. So this is your 4.4 Ed Puzzle, part 1. We are actually going to start on page 22. So go ahead and turn to page 22 of your packet. All right, so it says, let's try what we know about simplifying rational numbers to simplify rational expressions. Fill in any missing part of the fractions below. All right, so what they're showing here is they show you how you simplify a fraction. Now, there are different ways to do this, but one way is to bring it down to its prime factorization. If you guys remember doing like factor trees back in elementary school, you just keep breaking down the numbers until you get down to prime numbers. And what they do is they show you breaking it down into the factors, and then you cancel out any common factors. So we had a 2 on top and a 2 on the bottom, so those canceled, and a 3 on top and a 3 on the bottom, and those canceled. So you're left with 2 2s on top and a 5 on the bottom, which will give you a 4 on the top from the 2 times 2, and then the 5 stays on the bottom. All right, so we are going to try the same thing, but with rational expressions. All right, so if you notice, the first thing they do is factor. They factor the top and they factor the bottom, right, in this step here. So we're going to do the same thing. We're going to factor the top, and then we're going to factor the bottom. Now, if you look, they've already factored the bottom here for us, so we just need to factor the top. So we need to figure out what multiplies to give us a -6 and adds to give us a -1. That is going to be x minus 3 and x plus 2. All right, so that is how we would factor that. Now, the next thing we're going to do is see if there's any common factors we can cancel, which there actually is. All right, what would be the common factors that I can cancel from the top and the bottom here? So we could cancel the x plus 2 and the x plus 2. All right. Oh, I guess actually we could they want us to cancel it down here. So if we have our x minus 3, x plus 2, x plus 2, x minus 2, they want us to cancel these guys. Awesome. And then we're left with the x minus 3 on the top and the x minus 2 on the bottom. So you can see how you can simplify these expressions. Now, you can only simplify them, though, if you have a common factor on the top and the bottom. All right. Now, let's go ahead. We will try number 5. All right. So, again, we need to factor the top and we need to factor the bottom. So, for the top, we need to figure out what multiplies to give us 15 and adds to give us an 8. So I want you to think about how could you factor this top expression. What multiplies to give you 15, adds to give you 8. I want you to factor this expression. So to factor this top expression, you're going to get, x plus 5 and x plus 3. All right. Now I want you to go ahead and factor this bottom expression. Try factoring that bottom expression. So you should get x plus 6 and x plus 3. All right. So now we'll go ahead and we will rewrite this down here. And I want you to look, what factors can I cancel from the top and the bottom? So you should be able to cancel the x plus 3 and the x plus 3, which would give you the x plus 5 over the x plus 6. All right. So number 6 asks, why does dividing the numerator and denominator by the same factor keep the value of the expression the same? So basically what it is it's the same as dividing by 0. Oops. Oh my God, it's the same as dividing by 1. Oh my goodness, sorry. It is the same as dividing or pretty much multiplying by 1. All right, and really the reason for that is like if you look here, right? Well, what is 2 over 2 equal to? That's equal to 1, right? 3 over 3 is equal to 1. So it ends up essentially turning into 1. I guess I should say dividing / multiplying. All right. So, and that's what's happening here. All right. If you had an expression that was just simply just x plus 2 over x plus 2, right, this is basically 1. All right, and that's really what's going on here. There are some kind of domain restrictions you need to worry about, but that is essentially 1. All right, so for number 7, it says, if you were given the expression x over x squared minus 1, would it be acceptable to reduce it like this? All right, and the answer is no, and I'm going to show you why. Okay, so think about it this way. If I gave you something like, let's say we said like 3 over, I guess even we could do 9 minus 2. All right, that would give us, well, that might actually end up, how about this? Let's do 12. I know for sure that won't work. Ah, stop it. Okay, let's say we did something like this. Okay, technically, right, 3 goes into 12. If I did this, which is wrong, all right, I could get 1 over 4 minus 2, which would give me 1/2 there. Okay. Now, if you were to plug this into a calculator, 3 divided by 12 minus 2, you get 0.3, which is 3 over 10. So you can see that that does not work for numbers, really. So that's not going to work for expressions either. Okay? And really the reason for that is the factors are not the same. If I try and factor this bottom, this is one of those difference of squares ones. So I could factor the bottom into this. All right. These don't cancel with anything on the top. All right. Now it's factored, but I can't cancel anything. So you can't cancel because the factors are not the same. All right. All right, so let's go ahead. We'll try number 8 here. It says, given x squared minus x minus 6 over x squared minus 4, predict the vertical and horizontal asymptotes and find the intercepts. All right. So let's go ahead. Let's factor this, right? We have to factor this guy. So the top we can factor into x minus 3, x plus 2. And the bottom we can factor into x plus 2, x minus 2. All right. And it says predict the vertical and horizontal asymptotes. So we know that to find the vertical asymptotes, right, we set the bottom equal to 0. So if we set these bottom guys equal to 0, we get x equals -2 and x equals 2. Oops. All right. And then we know to find the horizontal asymptote, we first need to figure out, we have to look at the, not the powers, what's the word I'm looking for here? The degree. We have to look at the degree on the top and the bottom. So this top one's degree 2, and this bottom one's degree 2. So when the degrees are the same, you need to look for the coefficients in front of the x's. All right, so that's actually a 1 and a 1. So our horizontal asymptote is 1 over 1, or y equals 1. All right, and then it asks for the intercepts. So we'll find the x-intercepts. All right, to find the x-intercepts, we set the top equal to 0, and it's already factored, which is nice. So we're going to say x minus 3 equals 0. And x plus 2 equals 0, which is going to give us 3, -2. So we're going to have 3, 0, and -2, 0 as our x-intercepts. All right? And then for our y-intercept, all right, sorry, that's my ice maker. For the y-intercept, we need to plug in 0 for all of the x's. Now, I had someone ask me the other day, they're like, well, do we have to plug it into this one, or do we plug it into the factored form? It literally does not matter. Personally, I like to plug it into this one, just because it ends up being a little less work, in my opinion, but it literally does not matter, so you can plug it into whichever one you'd like. So we're going to plug in 0, minus 0. So 0 squared minus 0 minus 6, all over 0 squared minus 4, which is going to give us 6 over 4, which is going to give us 3 halves, sorry. All right, so our y-intercept would be 0, 3 all over 2. All right. So we've got number 9. Use technology to view the graph. Were your predictions correct? What occurs on the graph at x equals -2? So let's go ahead. Let's graph this on, you know what, actually I'll just make it big here. Sorry, I was tutoring someone in geometry there. All right. So we've got x squared minus x minus 6 divided by x squared minus 4. Oops, my goodness, what am I doing? Close parenthesis. All right. So if we look here, right, if we're trying to look at our asymptotes, oops, let's see. There we go. Okay, I'm trying here. We said that we're going to have a vertical asymptote at x equals 2 and x equals -2. All right. Well, if you look at -2, we actually don't have a vertical asymptote here. Right? Do you see how there's no vertical asymptote at -2? Now let's see if I put my pen there. What does it say it to, though? It says undefined. Right, -2. I can't keep still there. You can see it did say undefined. There we go. -2, undefined. So it's actually undefined at -2. All right. So let's go back to our questions here. Only one of these vertical asymptotes held true. It says, use technology to view the graph. Were your predictions correct? What occurs in the graph at x equals -2? So we know that there is a vertical asymptote at x equals 2. That held true. But not at x equals -2. All right. What we call that, remember how we had like -2, undefined? That is a hole. All right. And the way that we typically draw holes on graphs is, let's see, I'm just going to do a very terrible graph of this. Right, we had our thing there. We'll make this -2. Our horizontal asymptote goes there. We had something that looked like this, right? You draw like a little, when you draw the graphs of things that have holes, you draw a little circle there where the hole is. All right. So that is how you kind of signify a hole. All right. And how do we know a hole occurs there? Well, if we look back, look what happens. You can actually simplify this to x minus 3 over x minus 2, right? Those x plus 2's cancel. So if you have a 0 on the bottom that cancels with something on the top, that actually ends up making a hole, not an asymptote. All right, so kind of a new thing there. All right. So it says rational numbers can be written as either proper fractions or improper fractions. All right. So describe the difference between a proper fraction and an improper fraction and write 2 examples. So first off, this kind of brings us back to middle school here. So a proper is when the numerator is less than the denominator. All right. And then an example of this might be like 1/4, 2/5. All right. And then improper is when the numerator is greater than the denominator. So that would be like 5/2 or 11/6, right? When the top is bigger than the bottom. All right. So it says a rational expression is similar, except that instead of comparing the numeric value of the numerator and the denominator, the comparison is based on the degree of each polynomial. Therefore, a rational expression is proper if the degree of the numerator is less than the degree of the denominator, and improper otherwise. In other words, improper rational expressions can be written as a of x over b of x, where a of x and b of x are polynomials, and the degree of a of x is greater than or equal to the degree of b of x. So really, I feel like that was a lot of words. All you're doing is you're looking at the degree. Okay, here we have a first degree over a second degree. Okay, so we have small on top, big on the bottom. That's going to be proper. All right. So here, let's look at this next one. What is the degree on the top? What is the degree on the top here? So the degree on the top is 3, and then the degree on the bottom is 2. So that is going to be an improper. Why is it improper? Because the degree on the top is bigger than the degree on the bottom. All right. What's the degree on top here? So you've got second degree, and then on the bottom, we've got a fourth degree. So this one is proper. All right. Now, this one is tricky. Let's see, actually. You know, this one, we'll get back to you on that one. All right, this one here, let's see, this will be our last one. We've got x to the third on top, so that's going to be a third degree, and then the one on the bottom is going to be a first degree. All right, so this actually should give us a improper. All right, so now I want everyone to go ahead and flip to their Go problem 19. We're going to chat about that one. All right. So it says state the domain of the following rational functions. So remember kind of when you're doing the domain, you can't have any zeros in the denominator. You set these equal to 0. Oops. So x cannot equal 2 and x cannot equal -5. All right. So then for 19a, it says each of the previous functions has only one vertical asymptote. Write the equation of the vertical asymptote for 19, 20, and 21. So we're just going to do it for 19. So if we look here, it says, well, only one of these guys are vertical asymptotes. Well, you can see that this actually cancels, and you do end up with only x plus 5 on the bottom. So your only vertical asymptote is going to be x equals -5. X equals 2 is not a vertical asymptote. All right. X equals 2 is a whole. Right? Remember, when they cancel, they're no longer vertical asymptotes. They become a whole. So it says, for each graph below, sketch in the vertical asymptote, put an open circle on the graph wherever it is undefined. So we've got our asymptote there at -5. And then at 2, we have a hole. So you would put a hole there at 2. All right. So just to reiterate, when they cancel with the top and the bottom, you get what's called a hole, and you no longer have a vertical asymptote there.